Hi, guys, and welcome back to another episode of Women in Math and STEM, where our mission is to reach out to as many professionals, aspiring professionals, students, whatever you name it. We try to reach out to them, who essentially support the initiative of bringing more women and young girls into the STEM field. So, with that being said, as always, feel free to open up the description or transcript to better follow along, and I hope you enjoyed this episode. Hello, and thank you so much for coming to this call today and talking with me. Just to sort of start off, do you mind briefly introducing yourself and sort of walking us through your academic and personal journey to get you where you are today?
Yes, absolutely. Really happy that I'm able to do this. My name is Kaitlin. Um, I am currently a machine learning for education researcher at Tufts University, but my trajectory has actually been predominantly in physics. So to walk through that just a little bit, I'm from Florida. I graduated from high school in Florida and I moved to Stevens Institute of Technology in order to study physics as an undergraduate. I really wanted to study the world. That for me felt really important and interesting at the time. And as a physics major, I got to take many classes that would help me understand the world from, kind of how refrigerators work to how do quantum particles that we can't even see work. And it was in my undergrad that I did a very important internship in an area called quantum computing, which is basically this area of how do we build a computer out of these tiny atoms that we can't see. I ended up pursuing a PhD in the field of quantum computing at Oxford University. And once I got my PhD, I realized that actually something that I care about more than learning quantum mechanics is how I and other people learn quantum mechanics. And so that kind of encouraged me to want to pivot my research. And here I am, a postdoc at Tufts, thinking about how students learn, but still incorporating machine learning for my PhD.
I think you mentioned that you were originally inspired by physics because you want to study the world. I was just wondering, what is sort of like your favorite part after like studying physics and quantum computing and machine learning and education?
So what's really interesting is that when I was a physics major, the thing I hated the most was classical mechanics, which is basically the study of how every objects work or how everyday objects work. What was more fascinating for me at the time was quantum mechanics, like how do these tiny objects that we can't see work? How do we use them to store information? And I still think that that's very fascinating. There's a lot of interesting things about physics. I never really got to dive into cosmology, like the study of the origin of the universe or the study of space and kind of matter in space. That would be something I would love to study someday. But right now, I actually am going a little bit more towards classical mechanics, which is why I bring this up, because what I'm studying is how students learn about everyday objects and how students learn classical mechanics, which for me is now becoming very interesting and fun. So maybe my favorite part is all of it, which is kind of a cop-out answer. Um, but I really enjoy thinking about, sure, I'll say kind of like two main things. I enjoy thinking about how humans perceive their environment, including everyday objects, and how they think everyday objects work. Um, I'm also then interested at the quantum level of how we store information, and we use that system of quantum nodes to kind of act as a computer that can help us do really interesting, solve crazy interesting problems that we haven't been able to solve yet. So I'm kind of more interested in quantum mechanics from an applications perspective, whereas I'm interested in classical mechanics from a kind of like a human perspective, like how do people think about objects in their environment?
Sounds good. I was also just curious about like what a day in your life sort of looks like.
Yeah. Maybe we'll do today as my example. Today was quite a busy day. I'm an early bird, so I woke up at 6. I'm into the research group kind of office by, let's say, 7:30 a.m. I'm a huge coffee drinker, so I definitely get my coffee in the morning on the way to work, and it's like a part of my structure in the day to day. And I started off with a research meeting at 8 a.m. With a colleague of mine, and that maybe lasted about an hour and a half. A lot of my days will have, maybe at least 1 to 2 research meetings. I really love talking with people about research. I really love the collaboration aspect where we get to throw out different ideas together. So I had that meeting to start off my day. Then I had a bit of time for myself, maybe about 2 to 3 hours to think about some of the current problems that I'm working on, more as solo time. After that, my group had a group meeting at noon. And for group meeting today was really fun and exciting because we talked about the process of how we do science in the group. So we spent a lot of time kind of thinking about our philosophy of how we treat data and how we model our data, and how we form hypotheses and how we form questions. And that was very fun to think about that out loud with them. Following that, I ate lunch and took a bit of time for myself before a meeting with my advisor, where we talked about one of the projects that I'm working on. And now I'm here with you, and I'll probably spend maybe a couple more hours today with some solo time on my project, and then I'll go home and eat a nice dinner. But a lot of my days typically look like me really working a lot with other people, collaborating on ideas, having solo time to work on my research project, where that might be that I'm reading papers, it might be that I'm running simulations, it might be that I'm coding, it might be that I am coming up with a new idea. Right now, I am taking a look at an education data set, and I'm actually encoding that data set. So I'm coming up with a new encoding framework in order to do that. And so that's what I spent a lot of time on today. But my day-to-day will pretty much vary between me working on my project, collaborating with other people, and some research meetings. I don't like to have full days where I'm kind of on my own. I like social interaction.
Sounds good. I was actually surprised by how much like teamwork and collaboration there actually is because when I think of like science, I don't think of a lot of teamwork. So I was just curious, like when you say teamwork, like how many people are you working with and like what really happens when you guys come into like a problem or like a disagreement?
Oh, that's a good question. So a lot of my projects right now, my specific projects, I'm working with maybe one other person, max 2 other people. Most of the projects I've worked on, I've worked with max 2 other people. Sometimes you can have a larger group or a more collaborative project. For example, in my group meeting today, you could say that our project of the group meeting was to kind of come up with our own lab framework for how we think about data and how we think about science. And that was 6 of us coming up with that framework for the group. There's definitely a lot of collaboration. Scientists do not have to work alone. You can choose to probably work alone if that's what you'd like, but you definitely don't have to. And I would never actually advise anybody to. I think great ideas happen when you work with somebody else. And it's also very important to get feedback from other people to understand, even more so if your idea is a good idea. Definitely, I have good ideas. With other people, it makes them better. There's no doubt. Um, with respect to conflict, I think it's all about communication with the other person and ensuring that they feel respected and heard. I wouldn't say that there's a lot of conflict. I would say that a lot of us have, different opinions, and that's what makes us a really great group. We all come together with our different perspectives, our different opinions, and we are willing to share those opinions. And then we all can kind of, reason together to come up with something that we think is going to be overall best for the group. There's not a ton of, I don't know, there's not a lot of battling. I can tell you that. I think I'm very privileged that a lot of the people I work with are very empathetic and also very reasonable. And so we try to come up with a compromise that is going to work well for everyone. Yeah.
Sounds good. I think you also mentioned that you have like some experience in machine learning and also quantum computing. I was just wondering, like, what were some ethical concerns or like security concerns that are like typically addressed and like how you usually address them?
That's a good question. So I definitely don't work or didn't even work when I was more in quantum on the security side of things. Quantum computing is a very big field. And so there are people who work on the how do we make a quantum computer useful for machine learning? That's what I did. Some people work on how do we make better quantum architectures. And people do that from a theoretical perspective. They also do that working in the lab and actually, creating the quantum computer in the architecture and testing it out in real time. For the people who work on cybersecurity as an application, they've mostly worked around this idea of a very popular quantum algorithm called Shor's algorithm, which factors prime numbers. And so this algorithm was probably what kicked off quantum computing, maybe 15 years ago. Shor's algorithm, came out before that, but once we started to see that quantum computers could actually be built, people started to become afraid, because if we can factor prime numbers efficiently, then there's a large number of security systems in the US that could be solved efficiently or hacked efficiently. And right, if that's true, that poses a risk or a problem. However, there's a whole team of people who are working on something called post-quantum encryption, which is, okay, so if this does happen, what can we do? What can we, change our security system in some way? Is quantum going to give us an even stronger or tighter security system? So there's quite a lot of people who are working on ensuring that this will be okay. And I think a lot of people are not so afraid anymore of this being a fundamental problem in quantum computing. Now there's a lot more people who are interested generally in what can we do with a quantum computer. I would say that's probably the biggest open research question, is almost, okay, we are making this device, that's great. What are we actually going to do with it? What's it going to be useful for that's our classical fastest supercomputer actually cannot do? And this is predominantly what people are interested in working on.
Sounds good. Sort of a fun question. Where do you see quantum computing, or particularly your field, I think like quantum computing and machine learning, in like a few years or like a decade from now?
So I think quantum will probably have it's had its hype cycle, and I think it might dip, and then they will have another hype cycle. There's definitely a lot of promise in developing the computer and understanding how it's going to be useful and figuring out how it's going to be useful. There's a lot of exciting questions for researchers. Maybe in the next 30 to 50 years, we start to see an actual quantum computer that can do things that are out of the scope of reality right now. I'm not really sure what those will be. The goal, right, is that it can solve these problems that we think it would take maybe 1,000,000 years to solve. It can do it very quickly. There's this whole kind of realm of problems that computer scientists deem to be inefficient, given the time that we would actually need, or the data that we would actually need in order to be able to solve the problem. And so the idea is that maybe quantum can help with that. Maybe it can help us from a memory perspective. Maybe it can help us from an efficiency time perspective. And so it would be great in the next 30 to 50 years if we could start to see, drug molecule design processes becoming faster with quantum computers, for example. Or if we could see other kinds of machine learning algorithms, it can do something even greater because we have more memory storage for data, because a quantum computer can do that. These would be beautiful things. I suspect that maybe in the next 30 to 50 years, we're going to get something interesting. But what it's really going to take is not the theory people, but the hardware people, the experimentalists who are in the lab actually building the computer. Because right now, that computer takes up an entire room, similar to the way our classical computers did in the 1960s. That computer takes up an entire lab, and it's filled with these high-powered lasers, right? And things that are just very difficult for us to be able to get into tiny microchip devices and transport to people. So making this a realizable technology that is going to be useful and distributed is very difficult. And that is probably our biggest bottleneck. So if any of you are interested in becoming a quantum engineer, there's a lot. There's a lot of work to do and promise in that area, I think.
And sort of speaking on that note, I was just wondering if you had any pieces of advice, recommendations, suggestions, honestly, anything for students who are interested in physics and or quantum computing.
So my main advice point is going to sound really lame, and it's just to learn as much as possible and follow your curiosity and really enjoy that, because I think that, learning about physics is an opportunity to learn more about your everyday environment, to learn more about how your refrigerator works, how your microwave works, how your computer works. when you pick up an object and it falls to the floor and it interacts with the ground, why does that happen? How does it interact with the ground? Why does glass break? And why would a bouncy ball bounce back up? Right? There's different properties of objects that are going to influence the way the object interacts with everything. And so I think physics is just a beautiful opportunity to learn that. I think machine learning is a beautiful opportunity to learn about so many other things about data, and about how data is constructed and about how data works. My biggest advice would just be to really learn as much as you can and enjoy that process and enjoy the confusion that comes along with that process, because you're not supposed to know anything until you learn it. And that's kind of the point, is sometimes we all think that, oh, we should be experts or that we should already know this. And it's because we spent the majority of our life not actually recognizing when we were learning things, right? Like when I was a baby, I don't remember learning the word mom, but I learned it. And when we get older, sometimes we expect ourselves to have already learned something when we just haven't yet. So my biggest advice would be relax your expectations of yourself, follow your curiosity, and just really enjoy the process that comes with living in a cool world and getting to understand it more.
Sounds good. Thank you so much for coming today and sharing your experience. It was absolutely amazing. Thank you.
Thank you.